All right. So how do we compare two different machine learning algorithms, right? How do we compare learners? Well, let's look at a few things. So what I think has to happen. For example, if I have a patient and I have patient data about their temperature in Fahrenheit degrees, whether they have a runny nose, whether they have headaches, and whether they have chills, and that data can classify whether a patient has a cold or not, for example, well, the main thing is, well, let's say I have a patient with 104 degrees, yes to runny nose, no to headache, yes to chills. Does that patient have a cold, right? Well, I can classify the example, and this is the keyword, operating word here, classify, as having a cold or not having a cold. Now, what I'm going to call my hypotheses, in this case H1, is that a neural network can classify this data correctly. Alternatively, I can say another hypothesis H2 is that a decision tree can classify this data correctly, basically as a human has done, right? So this is the language we're going to use. We're going to use the language of hypotheses to indicate machine learning algorithms or learners, right? We're going to do classification to indicate labels here, and we're going to talk about data and examples as, this one person. So again, the idea would be which hypothesis to use, which learner, right? And I want to fine-tune my learning algorithm to a certain point, right? And then I have limited data. Data is not infinite, right? So all these are my constraints. I want to fine-tune my algorithm, but I also have limited data to work with. So how do I work with this? Well, I want to estimate the accuracy of future instances, and this is key. What I want to do is, I have some data. I'm going to train my learner on that, and I hope it works in the real world when a real patient comes in, for example, in the previous example, right? When a real patient comes in, right? That's a future instance. It's something that I have not seen in my training data for that algorithm, okay? So I have all the diagnosis with temperature, runny nose, and all that stuff, right? And then what happens is that I have to use that to train a machine learning algorithm so that it can accurately judge new cases or future instances of people coming with, some or all those symptoms. So there are various target functions, for example, right? So the target function is what I want to predict, right? So I don't know, people who like coffee, who play tennis, who are sick, who have a cold. That's the classification, right? Now, an instance X of the data set X, big X, is described by a set of attributes, just like the runny nose and all that stuff, right? So I'm just formalizing what I gave you before. Now, here's something that is key. The people that drink coffee, that are sick, that have a cold, that play tennis, they follow some probability distribution, okay? A probability distribution is the way they behave probabilistically. So with these symptoms, there's certain probability of having a cold. With these other symptoms, there's a different probability of having a cold. All those things start to form a probability distribution, okay? For example, income has a probability distribution. So a lot of people, there's very few high income earners and a ton of low income earners. That's a probability distribution. So what is the probability that you are a high income earner, right? That follows a probability distribution in reality, in the real world, okay? The idea, what I want is to train a learner, right, on independent examples, independent instances that I have somewhere that I've collected from the real world, basically from this distribution, and with a target function. So basically with a class that has been assigned accurately by something or someone in the past, right? So for example, I can have examples of patients taken from a hospital, so that would be a real distribution, right? And the function, the diagnostic is what the doctors have said, right? That would be some data in which I can train. Now, Given a hypothesis, H, and n random examples from the distribution, what would be the best estimate of the accuracy of my learner or hypothesis for future examples, right? This is the key question. I don't have those future examples, but I need to estimate whether my learner is good and it's going to work on future examples, right? So one of the things that we do is we look at the error of this estimate. So very quickly, right? The true error of my learner would be if I have a hypothesis over data from this distribution, all of the data from this distribution, right? The true error would be the probability that the prediction of the doctor is different than what my learner said, right? For all these data. That would be the true error. However, I cannot know this for all the people in the outside world. So what I can do is I can estimate it, and that estimation is called the sample error. The sample error is basically the error of the hypothesis tested on a smaller sample that follows that distribution, right? So they're not made up examples. They're examples of hopefully of real people or simulated following the probability distribution of real people. And what I do is I take the average of what the doctor said or what the doctor says and what my learner says. If they're different, I will put a 1. If they're equal, I will put a 0. Therefore, this is the average of all the cases that are different divided by the number of total cases. Now, I'm going to go over one example in a second. Now, let's look at problems when estimating error. Well, if you train on data from a hospital, for example, if S is the training set, right? And I train on that hospital error, and I train my learner on that, and my learner learn based on the hospital data. And I try to run that hospital data again to see if the hypothesis, if the learner learn well, that's optimistically biased, meaning I am testing in the same data that I used to train. And that is an optimistic estimation of the error because I use the data to train, so my trainer is going to work really, really its best on that data. So if I test the error on the same data that I used to train, then I'm biasing my error computation, right? I need to test on a different sample, a sample that I have not trained on, but that is representative of the same data that I trained. Basically, the bias is the error in the sample, the estimation of the error in the sample minus the error in the real world, right? And if I train and test on the same sample, this difference is just going to be very big. For an unbiased estimate, like I said, you have to pick a learner and the sample to test with independently, right? And the sample has to have the same distribution as the data that you train with, right? And hopefully both have the same distribution, which is the real world distribution. So, and the variance is how much error is attributed to the learner, right? Now, for example, if a hypothesis H, so a learner, right, misclassifies 12 out of the 40 examples in the test sample, we'll say that the error of the sample is 12 over 40 or 0.3, right? That would be the error of the sample that I tested. So it's not a hard computation. It basically follows this formula here. If I misclassify 12, that means that 12 times my hypothesis was different than, produce a different result than the human, for example. That's the number 12. And then divided by n, which would be the number of total samples. So now this is the sample error. What would be the error in the world? Well, we do an experiment. We choose a sample S of size n according to the same distribution that governs the data. We measure the error, right? And we measure that error, right? And we use it we're going to do some statistics, right? So we're going to say that this is the result of my experiment, this error, right? And we assume it's an unbiased estimator for the error of the sample, the error in the world, right? So again, the question now, I formalize the question a little bit more. What can we conclude about the error in the world? Well, for example, if S contains n examples drawn independently of the hypothesis and each other, and let's say that n is greater than 30, we're going to see why these conditions. Well, we can say that approximately 90%, with 90% probability, the error of the world lies in this following interval. It lies between the error of the sample plus or minus 1.96 times the square root of the error of the sample, which was, I don't know, 0.3, times 1 minus the error of the sample, which in this case would be 0.7, divided by the total number of examples, which in this case was 40 in the previous case, right? So this is a formula that will tell me the 90% of probability where the error in the real world is. Now, to compute, let's say 90% probability is too accurate. I want like 80% probability, right? Well, again, the formula is the error of the sample plus or minus some multiplier. It was 1.96 earlier, right? So plus some multiplier plus this square root expression. Now this multiplier varies. If I want a 95% confident, 95% probability that the real error, the true error, right, where the true error is, I will multiply the square root by 1.86. If I want a 99% accuracy on the true error, I would multiply the square root by 2.58. If I don't care, and I just want a 50% error, I would multiply the square root by 0.67. Now, where do these come from? Okay, these come from the normal distribution, okay? So if you're following the slides, I have a set of slides that explain how do we get here. So these classes are yes or no. So you have a cold or you don't, right? That is usually governed by a binomial distribution. But when the examples in the binomial distribution start to grow and they become large, okay, the binomial distribution becomes what's known as a normal distribution, okay? And in a normal distribution, the mean of the error is an approximation of the true error in the world, and the standard deviation of the error is usually the standard error times 1 minus the standard error divided by n. Now, in an approximation where we don't have the error of the world, we will use the error of the sample for these to compute the standard deviation. This is basically a whole set of slides just to indicate where we were before, where that radical term comes from. Now, if we have a normal probability distribution for the error, the expected error is the mean of the errors, right? So the average. The variance is going to be that sigma squared, right? And the standard deviation is just going to be the square root of that sigma. And like I said, you can get, this is a shorter form of the formula, right? You can get the probability of the confidence that the actual error is within the sample error plus minus a z multiplier times the standard deviation, which was that radical number. And here you have just a repetition of the other numbers. Now, here are some examples. You can pause and see that I get, for if S contains n examples drawn independently of the hypothesis and each other, and they're greater than 30 because it's a binomial distribution, but we have so many examples that it behaves like a normal distribution, 90% probability the error of the sample lies in this interval, right? So here we're approximating that, right? Now, because, And here's another thing. Because if you have identically distributed random variables, okay, and they're all governed by the same probability distribution with mean, mu, and the same variance, the same mean, similar mean and similar variance, the sample mean, right, and the sample mean is basically add each one of them divided by how many are there. This is an average, right? The central limit theorem says that when n, the sample size, gets larger and larger, the distribution governing that mean is a normal distribution with mean mu and variance sigma squared divided by n. So whatever this variance is divided by n. Okay? Why is this useful? Well, because if we want to compare, I'm going to skip this 2 slides, they say the same thing. Because if we want to compare learners, right, we can use something called the T-test, which works when the things you want to compare are normally distributed. So if we have a high number of examples, we can assume that our error is going to be normally distributed, and we can compare them with something called the T-test. So let's say, for example, right, we partitioned the data, right, into k disjoint test sets. Test 1, test 2, test 3, test 10, right? Let's test k. So let's assume it's 10. We partition our data from the hospital in this case in 10 equal bins of, whatever, however many examples on each, hopefully more than 30. Now, what I'm going to do is I'm going to go for each one of these test sets, I. So I'm going to go from 1 to k, doing the following. I'm going to get the error of learner A on test set I, 1, 2, 3, and so on, minus learner B, or hypothesis B, on test set TI. So for the first one, I'm going to use the first partition. I'm going to get the error of the learner on the first partition minus the error of the second learner on the first partition, and that's going to be D1. For the second partition, I'm going to get the error of the first learner on the second partition minus the error of the second learner on the second partition. That's going to be delta 2. When I is 3, I'm going to get the error of the first learner in the third partition and the error of the second learner on the third partition, and that's going to be delta 3. And I do all that for all the partitions, and then at the end I return the average error. And then with that in mind, I can be, again, that's going to help me compute, right, my confidence interval estimate for this error, right, for delta. So the confidence interval is going to be this delta average plus or minus what's called the t distribution times the standard deviation. The standard deviation is going to be given by this formula. Now computers can do all this. You don't need to do it. What I will say is k is the number of intervals that you decided to compare. Okay, it's called also the degrees of freedom, and p is how good a probability you want to be sure that this estimation is really there's really a difference between learner A and learner B. Okay. Now, what we want to do, right? What we want to do is basically compare this. But here's the thing. We don't want that optimistic bias of training and testing on the same thing. And also, we don't want to do this just one time, go through every partition and compare every partition once. We might want to do this many, many times, right? So here, for example, is a very common algorithm to evaluate learners, the k-fold method. So we have our data D0. I'm going to partition it into k disjoint test sets. Okay, so non-overlapping. So let's say I have my data and I'm going to partition it in 10 data sets. So T1 all the way to Tk. In this case, it'll be T10 of equal size, at least 30 for the number of examples. What I'm going to do then is I'm going to go for each one of these test sets, and what I'm going to do is I will use TI. So the first time I'm going to use T1, the second time I'm going to use T2, then T3, and so on for the test set. And what I'm going to do is I'm going to train the learner with the remaining test sets. So for each test set, right, I'm going to keep TI for testing. For training, or for my sample, I'm going to keep the whole data set minus that partition. And then my hypothesis A is going to be learner A trained on that data set. My hypothesis B is going to be the learner B trained on that data set. And I'm going to get the error of each one of these learners on the partition that I selected to test. Then I go again the next iteration and I do the same thing. I select, say, the second partition to test. My training data is going to be the whole data minus the second partition. So it's going to be partitions 1, 3, 4, 5, 6, 7, 8, 9, 10, for example. And again, I train 2 learners on this and compute the error, in this case on partition 2, the second. For the third iteration, same thing. The partition that I'm testing it is the third one, the fourth one, the fifth one. And what I'm training on is all the remaining partitions. So in this case, we're not just training the methods and comparing it across 10 partitions. We're training the learner every time with all the partitions minus the one that we're using for testing. And then we test in a partition that we have not seen, because the test partition we haven't seen. We're training on everything but the test partition, right? So we do this multiple times, and basically we just average the errors that we get at the end. And that is a great approximation of the error outside in the real world. Now, sure, many of the learners we're training every time on everything but one partition. So our training has a lot of overlap. So it's not perfect, right? But this approximation is better than no comparison at all. And our data is limited. Remember what we said at the beginning, right? At the beginning, we were talking that we need to fine-tune our learning algorithm, and we do that by training it multiple times. But also we want to leave some test data where the learning algorithm will never see that data, right? But we also have limited data, so something's got to give. And the k-fold cross-validation method is a really effective one to actually test algorithms. And we will get this delta, and then we can run a t-test and find what is the probability that one algorithm is better than another. That probability, right, which the computation was here, but really computers can do this, that probability is going to tell us if that probability is above 95%, we'll say that there's a significant improvement or decreasing, or right, there's a significant difference between the first learner and the second learner. Thanks for watching. Stay tuned. I'm going to give an example of how to do this on an off-the-shelf tool called Weka.